All right, so today we're going to cover the second module about the optimization for linear regression. And just to get this is kind of a review of what we covered last time. So we worked on this super simple function, which is a quadratic function, has only one input. Its LW function is W quadratic minus 3. And then we actually emphasize the very important idea. So the gradient, because actually in this case is derivative, because there's only one variable. So when you have multiple variables, that function versus all the variable create that partial derivative together create a vector that's called gradient vector. So that's actually what we showed before, is this JW, if you still remember our concrete example, versus the W, that can be the first in the vector. The second is the B. This create a vector, include two partial derivatives, and each partial derivative is your loss function versus one of the variable in the variable vector, and this is called gradient. Gradient vector. So the number of parameters, the size of these variable vector is the size of your gradient vector, and gradient always pointed to the direction that your function increased the most. So in this case, so at every point at this side, gradient, actually here is derivative pointed to the right. It's the direction function increased the most. So we want to minimize the function. That's why we go to the opposite of the gradient, opposite of the derivative of this case. So that's why gradient descent makes sense. We are going the opposite direction of gradient, and then gradually, and then so that we are approaching, we are more and more close to the minimum points. So we actually show you this. We can start from 2, and then we take the derivative, which is minus, which is the 2 times 2. And then our learning rate is a hyperparameter user defined. In this case, we define it as 0.1. So together, and then starting from the 2, we go the opposite direction, which is the 2, which is go to the left. It's 2 minus 0.4 step gives us 1.6. So we jump from 2 to the 1.6, from WK minus 1 to WK. And then from WK, we go further, taking gradient, taking derivative at that point. The gradient or the derivative is 2 times 1.6. So you always need to update by that current point's gradient. So it's 2 times 1.6 and then times the 0.1 and take an opposite direction. So this together, again, going to the left, it jump from 1.6 to 1.28. So you can just keep going further and further, and then this, because this is such a great function, it's just there's only one unique solution, and this learning rate, it's also not too large, so it actually can guarantee your iterative optimization can converge to that optimal point. In this case, in fact, is 0. So this is a W star. All right, so this is really simple gradient descent. So I got my clicker. So feel free to ask questions on the chats. At this point, because this is like the most important, this is like most important for implementing your homework 1. Right, got my clicker on. All right, Okay, so now we are going to use gradient descent and a variation version of gradient descent called stochastic gradient descent to solve our linear regression training task. So let's, again, first thing to do to use gradient descent is to figure out the loss function and taking the gradient of that function. So this is our loss function. Just to review, and this basic linear regression, its loss or its cost function, it just is 1/2. Take summation of all the training data, and on each data we use the square of its area of those predicted fxi minus the yi. We can rewrite this summation of areas and into this matrix vectors multiplication form. And then to use gradient descent just very easily, the first thing is to take gradient of this function, right? Let's see how do we do it. All right, so I have a little bit abuse of notations here. So gradient is normally written as this notation. It's a vector, and it equivalent to, so don't worry about here. You can just see this is like theta 0 onto maybe theta p. Just like what I showed you in the previous page, for all of the weights you need to learn, you take partial derivative of your cost loss function versus that specific parameter. Then together, and each partial derivative all put together, stack together, you got a vector, and this vector is called gradient vector. And so in this case, it's actually very easy to take just from this summation form, right? When you're taking the gradient, if you still remember, so you can almost use everything you learned by taking the derivative to this gradient case. So you can just, when you have a quadratic function, take gradient, take derivative, you actually put the 2 before, and then that 2 canceled. So this is the reason why we have a 2 here, 1/2 in the cost function. And then you take further insight, because you actually copy, so that first step is really here, and this is the gradient of this quadratic. And then because our parameter is x transposition theta, right? This is a linear form. When you're taking the gradient of that quadratic, this inner product form, it's really just the linear form, right? What you get is the coefficient. So in this case, that coefficient vector is just xi. So it's not totally, there's still, you can see there's a little odd why there's no transposition. It's because of the, you need to, when you concretely do it, I mean, then it actually, because to match the multiplication size, it's not the transposition, you put it on the right. So this is actually very easy, but it's a little abusing of the notations. So I actually rewrite it here, but what we truly used, so then you just put this gradient vector formulation into the gradient descent algorithm, if you still remember what is gradient descent. So let's review the one we used before, xk equals to xk minus 1, or maybe double OK we used in the previous, which is not to confuse with the x, just that WK equals WK minus 1 minus, because we want to go to the opposite direction, right? And then the gradient term, gradient of versus that term versus the loss function. Let's just put the loss function here, and at that versus the W, at that WK minus 1, the gradient values. So let's just copy the term and then into this equation. What you can get is exactly this is. So theta t equals theta t plus 1 equals theta t plus alpha times, because there's a minus, right? You just put the minus inside the inside this the first part, and then you are going to get this gradient form. This is the gradient descent for linear regression. Very, very simple. But when you truly implement it, we actually not using this summation form. So I highly recommend you try to use actually this form, because as we explained before, and if you write as this summation form, if you implement it like this summation form, you are converting this operation into a sum operation, right? Which actually much more costly, time-wise costly, because you can't use this good like parallelization data structure underlying your computer. And it's much better to write this as the second line, which is the theta t plus alpha x transposition times y minus x transposition theta t, because your underlying BLAST library, NumPy, and then using the BLAST library can do much better, much quicker, and also memory efficient operations compared to you if you implement do this summation of 1 to n sums. So this is a recommendation, but if you can't figure out how to do, you can also do the second way. Second way is easier to implement for sure. Yeah. All right. So if you want to understand how do that summation of all the n terms and times this 1 minus x transpose theta times x related, how to convert that into the matrix form, I have the concrete derivation here. And this is really about how to get gradient of a quadratic function, of a linear function, and then you just put it together. So this is extra, but feel free to check it out if you want to be able to derive this. So this together is called a batch gradient descent algorithm to solve least square linear regression. And I want to do a little bit deep diving of this looks kind of weird form. So let's actually look at this. So what is this part? If you think about that part, and it's really just, so let's write it more clearly. So the y, this is the y vector, y1, y1, y2 onto the nth training vector minus, and we actually did this derivation. You can, because this x times the theta t can be put inside, so it's, in fact, this is just x1 transposition theta put at a column vector representation, and then x2, this is your second sample, and column vector representation onto xn, this is your nth sample, that vector representation. So yeah, maybe more clear here. So actually, yeah, it's actually very much more clear in this page again. So let's look at this part. If you look at this part, what is this? This is really just the error term. This error term, how your prediction and the line, this linear regression prediction, the differences. And this differences is used as a weight to weighting that specific samples. And your gradient vector, you can think about it's more like a weighted summation of all the training samples. And those weights are decided by the errors made by your prediction. The larger the error, the more parts, the contribution of that specific samples to the gradient vectors. And this actually makes sense, right? If your x is predicted very correctly, you don't need to adjust the gradient at all. And it's more like an ensemble of opinions. Oh, you predict really nicely on me, then I don't agree. I don't want you to change at all. But if you predict very badly on me, I want you to change. I want you to change a lot. So this is actually very intuitive, this gradient term, if you think about it. So more error, more contribution of this X sample to the gradient, to the change, to the change of the parameters. Question about here, so you can type in the chat. I think this is a very important intuition about understanding gradient descent. All right. Okay, so let's see. I always like geometric views about the loss function and how your optimization works on this geometric views of the loss curves surface. So when we think about our the loss function, like J theta function, so we actually cannot plot, like visualize more than 3-dimensional. Let's just think about 2-dimensional. So we have like 2 parameters, and which is like theta 0 and theta 1, and we visualize the loss function as the this y-axis or maybe z-axis in this case. So as we emphasized before, this least squared loss function is a really good function. So it's more like a bow function. So all parts are higher and then go together into a valley, and that's the valley. There's only one lowest point. That middle of the valley is your best position that have the smallest loss function. And so people normally like, so this is difficult to, so this is normally called a surface map of a function. And then people actually normally plot you not the surface map, but something called contour map. So let's look at the contour map. You can think about contour map is you start from like, you look at this bow, this quadratic 2-dimensional function from above, up above, and then looking down, and then project all those points have the similar height, had a similar loss function into the same contour in the 2-dimensional space. That's called a contour map. So in this contour map, you can tell. So we use the lighter color. Lighter blue means the lower J theta function. Darker purple color means the higher loss function, and the more into the middle of that contour and the lighter of the color. So the contour map, and you can think about contour map, it's a good 2-dimensional summary of your loss function. All right, so yeah, so I put this, you can think about the 3-dimensional view of loss function on the surface map is like a bow, and the contour map is if you flip the bow, let the bow look at you, and then you see the bow, and then everything like on the same height of the bow create a circle, create a contour. So what people normally show you of gradient descent are not in the surface map, but actually on the contour map. And also we also need to consider like truly how my parameter truly moves. It's indeed in this contour map created to the 2 dimensions that is theta 0 and theta 1. So my theta truly moves in the theta space. It doesn't move in the J theta space. It needs to be very clear. So because I'm moving in the theta space, resulting my loss function becomes smaller. So I hope this is clear. So always gradient descent, gradient moves in the parameter space. It's really a space. It's really a theta. It's a move in the parameter space. That's the very critical point to think about gradient descent. All right, so Jack, you're helping me to answer the chat function, right?
Yeah.
Okay, perfect.
It was helping too.
Great, yeah. Okay, so this is critical, and then so again, so I know I'm like emphasize this again, but just because it's very critical for now, for homework, and also for your later, like all the deep learning based gradient descent based approach. So really the fundamental understanding of what is gradient is extremely important. So again, gradient is a vector. Gradient vector points to the direction. Gradient is a change in the variable space, in the theta space, in the theta variable space. It pointed to the direction of the greatest rate of increased function. And its magnitude is the slope of the surface graph in that direction. All right. Okay, so this is normally people show you the gradient descent and they show you a contour map. So this is a pretty good contour map. So they actually use darker color in the middle and then lighter color the further, the lighter. So created this kind of 3D fake feelings. The middle is lower. So I hope you like appreciate this graph. So you start from a theta 0, and then you just calculate the opposite of the gradient direction. You stepped that direction times the alpha, which kind of controls how far you go by every step. That every step you jump is the minus alpha from that theta k that you just were, minus the alpha delta, the gradient at j theta t, theta t. So it's actually so like write it. So this is theta 0, and at this step you use alpha, okay, gradient j theta t. So every step you need to update that gradient you use the current gradient vector direction. And this can help you to find a local minima of a function. And so I already talked about this. All right. Okay, so this is again the surface map view, a contour map view. We already emphasized 3 times, so like we'll skip this page. So you need to implement this. So in our homework 1, and this relies you to use some functions from the NumPy. I already actually did a very quick review about NumPy. So here are 2 good links about one is the NumPy cheat sheet. It's a very concise view about the different kind of basic functions, and we need to use a little bit more advanced. So especially the normal equation based that version. So check out the menu, the NumPy, this link I provided to you. And very importantly, when you do this is you want to match the size. So in this page, I actually show you what should be the right size, right? So for example, like this operation x theta t, and the x is training data, is n times p times 1, together it generates n times 1, and then this y vector, target y vector, because there are total n samples, so of course it's n times 1, and the generated x theta transposition should be n times 1 too. Otherwise, this minus operation is just will not allow you. If your code has errors, I think most likely is because of the match. The size of the vector doesn't match with each other, or size of the multiplication doesn't follow the right order or right transposition. Check out those. Just print out the size, and then you're going to understand very easy to debug what's the issue there. So this is the reason why I showed this really concretely. Why? So at every step, how the right size. Okay. Yeah. So your gradient vector is the same size as the parameter size. So just emphasize that one more time. Okay, so now the thing is, we actually talk about 3 things to be concerned about when you're using the gradient descent. So the first thing we try to emphasize is you need to be careful about the right learning rate. So in last session, we show you this one-dimensional quadratic case. So if you have too large learning rate, you're going to jump out of the valley. I mean, going to some positions has even higher loss. And this is similar in this figure, in this contour map view of the j theta function. Actually, j theta, if in the 2-dimensional, it's much better than this. but maybe some data, like so in a lot of this it depends on your data. So in a lot of cases, you may not, you most likely don't have as nice as a function like our j theta quadratic function. And in those cases, very careful, choose your learning rate very carefully, control. And yeah, because you really don't want your gradient descent kind of oscillate, not going to minimal, but maybe jump to like even higher the contours. Okay, so now I finished the batch version of gradient descent. I will talk to you about a very, very important stochastic version of the gradient descent called the stochastic gradient descent. It's actually super, super simple. So now let's review what we derived, right? We have this j theta function, which is just summation of 1/2 of all the areas over all the training data. Then you take a gradient. So your gradient actually have the form, still have this theta t plus alpha, using that most simple way to represent it. It's just a summation of all the specific terms from all the training samples. All right, so I think you can almost guess what is stochastic gradient descent. Stochastic gradient descent, it just, let's remove that summation terms. So rather than we calculate this term, this gradient term, after we have the results from all the training data, we don't want to wait. For every training samples, we just calculate that term. I immediately update my parameters. So it's really just remove this term. Nothing fancy at all. And this is called stochastic gradient descent. And this is extremely powerful method. We're going to talk about it later, but you can actually tell this is not my gradient, right? Because I actually did a calculation. The gradient of my loss function is the summation. It's a summation of all the training samples error contributed. That's the correct gradient. And this is only an approximation. This is only part of it. So why it makes sense? I mean, so first of all, like rather than wait to the so many samples, in a lot of cases, your training data maybe have millions of samples, right? Just calculating this is a lot of computation. And rather than wait to the end, we would just rather using some approximated versions, update my parameters earlier, because I have to update it anyway, right? So after I move from like theta 0 to theta 1, and I have to recalculate the gradient on theta 1 to move to theta 2, right? So get just an approximated version of that gradient of theta 1 is fine. I mean, because it just gives me more frequent updates. So this is one good reason of using stochastic gradient descent. So the other reason is, so like I told you, I mean, this is actually not, the summation form is not the one we used. What we used is, if I still remember correctly, I think is x, it's y minus x theta times x. Yeah, I think this is, yes, it is. Yes, this is the one. So yeah, let me check. Yes, it's alpha x transposition. There's x transposition there. Y minus x theta transposition. All right. And then there's plus alpha. So this is truly what I'm implemented. I feed this into my algorithm, right? So if this is too large, and there will be an issue, and this is like n times p, Yeah, this is 1 times n, this is n times 1. I want to guarantee this as, this should be transposition, otherwise it doesn't write. Okay, this should be transposition. Yeah. Yes, this is transposition, and then, yeah, I think x should be this side. Alpha, so this is x transposition, p times n times 1. This gives me a p times 1 matrix, or vector, right? So this calculation and also the memory cost, we actually did a review, in the last part of the linear regression. If this is too large, if this n is maybe like about millions, like 2 million points, and then p is super large too, p assuming like this is more about maybe 3K features, and there's no way we have this matrix in our RAM. And it's just not feasible for our computer to do this huge calculation using the batch style. So you just have to split it. And that's the other reason we need to use this kind of stochastic version, because our computer can't hold that large training data. That's the second reason. And the third reason actually is, so let's look at the stochastic gradient descent. This on the contour map and the gradient descent. So as I already told you, our function is actually really, really good. The J theta function is extremely good, but the majority of the machine learning problems, that loss function is actually bad. And the stochastic gradient, so bad in the sense there are a lot of local minima, and if your gradient descent just so greedy, so like into that correct gradient and go to this, it's very easy just stuck into some bad local minima. But stochastic gradient descent is very noisy. It's this noise, in fact, help you to jump out of the bad local minima. And that's the third reason stochastic gradient descent, it's actually good in the merit of, because that approximated gradient approximation helps you not stuck in local minimal too much. So 3 reasons. All right, so it's just, you can actually tell, single sample based stochastic gradient descent, just remove that sum totally. And batch version just calculate that summation over all the training samples. But I don't need to go too extreme, like just the 2 sides, right? There's so many things, like possibility in the middle. So I still keep that summation function, but that sum is not over all the training samples. It's over a subset of training samples. And this is called the mini batch version of stochastic gradient descent. And again, so just you add the summation back in there, and then you can still just write this in the matrix form to make use of, again, so we want to make use of the BLAST library, because in case we have like GPUs or good CPU sim architectures, and your calculation of this kind of summation can be parallelized, so which is actually very fast. So let me use a not completely correct example. So assuming you have 13, maybe 13 threads in your current computer, if you feed in this summation, each one of the thread, each one of the core can calculate the gradient, that specific gradient approximation for one sample in your batch, in your mini batch. And then they just all together got each one of this term, and then just there can be a summation function, just put them all together. And the cost, it's almost equivalent to a single sample. Because if you only just feed a sample at a time, you cannot use that parallelized architecture well. So I hope this convince you to use which version really depends on your current computer, the computer architecture, that what's the best for that computer architecture in your computer, and depends on the RAM size, depends on the CPU, depends on the GPU kind, and that help you to make a decision. Should you use the whole batch version? Should you use the mini batch version? What should be the right B? So it's really a balance of algorithm and also hardware considerations. All right, so let's again to review. Stochastic gradient descent are very useful when training with massive data because they may not fit in the main memory. So it's very useful for when training data arrives online. So this one I did not cover. So it's the force merits, because they may just not come all at the same time. They come like at some kind of streaming fashion. And for those cases, you can still use stochastic gradient descent to up your data, like up to your model, like constantly with more data, with more updating. And stochastic gradient descent can be used for offline trainings too. And what I covered is mostly for the offline training. And we actually mentioned, right, by repeatedly cycling through the whole data in the offline setting. So what we normally call AEPOC, what we meant AEPOC means your stochastic gradient descent or your mini batch stochastic gradient descent finish a whole pass over the whole data. So that means AEPOC. And again, you can think about mini batch stochastic gradient descent like a superset. When B equals to 1 is a standard single sample SGD. When B equals to N, it's a standard batch version gradient descent. All right, so yeah, I think I already covered this. So mini batch is much faster computationally than the single point SGD, because it can make use of the underlying computer architectures and the RAM size efficiently. And which one should you pick depends on your computer, the equipment, and yeah. So now I need to add this fourth point to be considered in using stochastic gradient descent and also gradient descent. So how do we stop? So because both of those are like this iterative optimization method, right? So how could I know when to stop? I mean, it's a very difficult question actually, when to stop. So far in our homework, we ask you to visualize the training loss. So it's actually not the 1/2 version, but the 1/n version. So here we call that mean square error loss. I actually reviewed it. This is one of the metrics people use to judge the regression performance. It's really the same as summation over all the training samples. That error take a square and take a summation, but now we are not doing 1/2, it's a 1/n. So the reason why we do 1/n is because so this homework we have only the training step, we don't have the testing step. So in the next homework, we're going to ask you to have the testing step, and then by that time, then you can mean square error on per sample level can be compared. The two curves can be directly plotted together. The training curve and a training loss curve and the testing loss curve. Those are really great sanity checking tools to understand how your iterative optimization behave in the training. All right. So this is easy to implement, and then what the curve roughly like this. You use x-axis at epochs, and then at each epoch you show the training error, the mean square error in this case. Of course, it should decrease, right? If your learning rate is reasonably controlled. Yeah. So when to stop? So most cases, we just predefine a maximum number of iterations. And there's also some algorithm use So they stop when the improvement of that training mean square error, like the improvement just drop below a certain threshold. But the majority actually use this maximum number of iterations, and we ask you to implement that in the homework too. So it's actually very tricky. So this iteration numbers is not a uniform, like universal number. One works for all. No, that's actually not right. It depends on your learning rate. So I'm giving you an example. This is my homework one, my Jupyter version. So like if your learning rate is good, relatively good, that iteration number should be enough to let your training loss converge. But if your learning rate is too small, it hasn't even fit very nicely, and I use the same iteration number to stop. It works for this learning rate, but it doesn't work for this learning rate. So you really need to take a look at your loss versus epoch curve to decide. So this is the reason why we asked you to plot it, take a look, sanity check, eyeball, and understand this. Hopefully this can help you understand like gradient descent and design concerns a little better. All right, so to summarize, we covered normal equation based, gradient descent based, stochastic gradient, and mini stochastic gradient and mini batch based SGD. They all have their pros and cons. So like I emphasized in the beginning, the normal equation based method is a single shot closed form solution, easiest to implement. But actually, in fact, you need to like implement this X transposition X inverse step, and this is for you easy to implement, but the behind those, the true code actually behind it is actually very numerically expensive, and also there's a lot of numerical computation needs to be considered, because in the case of matrix is singular. I hope you still remember what the singular matrix mean. But actually, like this way, it's a little problematic. But the other way, what I told you, like in the NumPy linear algorithm function, there's a solve function. They have a lot of strategies to bypass the singular matrix case issues. But we still ask you to implement this because our function is good, means very difficult. It's normally no, so our function is pretty good. You shouldn't meet with singular matrix issues in the implementation. All right, so we already talked about gradient descent. It's gradient descent versus the normal equation. It's iterative, right? And it's a batch version, and it's actually converges slowly. And the stochastic gradient descent, like just very apparent, right? So gradient batch version is to update gradient after calculating on all the training samples. It have only every epoch you have only one update. But stochastic gradient descent is really extreme version, and for every epoch you actually update n times of your theta. This is a much frequent updates compared to the gradient descent. Mini batch version is a little bit more frequent, but of course, like stochastic gradient descent, there's a lot of noise. It's much more frequent updates. All right, so it's fast because more updates and also less prone to local optima, but there's issues with convergence and maybe not always guaranteed. Okay, so there are actually a lot about gradient descent and stochastic gradient descent, and which we cannot cover in this intro level class. I share you this link and also this archive survey paper, so feel free to check it out. So there SGD, a very important SGD called momentum, other stochastic gradient descent method called momentum, Nestrov autograd, auto delta, and RMS probe. And also I show you this figure just to show you an example of stochastic gradient descent based and the gradient descent based. So the previous curve is gradient descent based. I think that's what, yes, it's kind of very smooth. And the stochastic gradient descent based is like this. All right, so I think this is all for what I want to cover for the optimization for linear regression. And